Hello everyone. So we are here in this particular video lesson. So on this lesson that we have right here, we were going to discuss the experimentations done with experimentations done by modern scientists or modern geologists in validation of the plate tectonics model. So in this case, what you will encounter in this particular lesson are the things that they did or the experiments that they did that validates or that supports the plate tectonics theory. All right, so basically we have three here. We have the ocean drilling, the hotspots, and the paleomagnetism. So each and every experimentation, we were going to discuss it one by one, and what makes them so significant in validation or validating the plate tectonics model. All right, so let's get started. Alright, so if you recall the scientific method, so in a scientific method, there's what they call an observation, a hypothesis, there is also an experimentation. After experimentation, there is an analysis and analysis of the data after the experimentation. And after the experimentation, after the analysis of the data due to the experiment, we have now the conclusion. So in this particular flow chart that we have right here, so 100 years ago, we have Alfred Wegener creating a hypothesis regarding the continents or about the continents that they are moving. Alright, so hence he called it the continental drift hypothesis, and we all know that continents do not drift on the water. So instead, this was rejected during that time, and until decades and decades after. So this some scientists or some geologists go back again to the idea of this hypothesis and verified it using modern day equipments. All right, so due to the invention of sonar, so if you know the sonar is an instrument used by some ships in order to map out the things underwater. So this sonar is used by some warships during the World War I and World War II. So this instrument is used to map out the ocean floor for some submarines. All right, so because during the World War II, submarines are these are nuisance to allied navy, something like that. So they use this sonar in order to find if there are submarines located on that area. Now, little that they know that these sonar instruments that they use, so sonar from the word itself, sound, navigation, and ranging, they use sound wave on this ship, and then they use these reflected sound waves that is bouncing from the ocean floor, and then obtain the data from it. And some geologists, they be able to draw something from this reflected data from the ocean floor. Now, using this sonar, they be able to find out that there are a lot of things that we did not find out on the first thing that Alfred Wegener saw on the continental drift. And using the sonar, they be able to find something else like seamounts, like ridges that are found in the ocean floor. Thus, after the use of sonar, intensive use of sonar, they be able to upgrade the continental drift hypothesis to become a plate tectonics theory that we know right now. And aside from the plate tectonics theory, there are other theories that supports the plate tectonics theory that we have right here, like the seafloor spreading theory. And upon doing some experimentation and investigation on this plate tectonics theory, so what we have here right now are the three things that will validate the plate tectonics theory. So what is the main idea, or what are the experiments used in order to find out that the continents are really moving? All right, so here we go. Okay, so we answered this one already. How deep can we dig? So, all right, humanity just achieved a 12,000 meter deep, 12,000 meter deep hole in a in an experimental drilling that happened long time ago in Russia. So this is the Kola Deep Super Borehole. Yan. So this particular experiment did not last long because of the temperature that is encountered by this drill as it goes deeper to the earth. Alright, so they only achieved 12,000 meters basically, and after doing so, they stopped the experiment and they left the area or they left the idea of digging the earth's crust hanging. All right, so how deep can we dig? So far we can dig around 12 kilometers or something like that, but we can't dig deeper than that. All right, so with that, all right, there are two scientists here that we have. We have Harry Hess and Robert Dietz. All right, so these two together, okay, together they develop a certain idea that as the continents move, somewhere along the ocean floor makes it possible. So they have an idea that in the seafloor, because of the intensive use of sonar, they be able to find out that something that is on the ocean floor that is spreading. So hence, they called it, or they call their idea, the seafloor spreading theory. So in this particular idea that they develop, it states that the seafloor spreads out along its ridges. Now, if you remember our discussion about three types of boundary, so they are talking, what boundary they are talking here? They are talking here the divergent boundary. All right, so the divergent boundary that is found on the ocean floor. So this is spreading ridges enables the continent to spread outwards and move them along the way. All right, so Harry Hess and Robert Dietz. Now, let's go to the first evidence. Right, so the first evidence that is supporting the seafloor spreading theory is the ocean drilling process. All right, so there are so many geologists who do this particular process called ocean drilling, and this particular process is the most we can consider this as the most convincing evidence in confirming that ocean floor is spreading. So how come? We can drill the ocean floor and find out based on the cores that we gathered from the ocean floor and study it, we can find out that the ocean floor is really spreading. All right, from the spreading centers in the divergent, or in the spreading centers located in the ocean floor. Alright, so in this particular experiment, they found out that the age of deepest sediments in the ocean floor, and also they be able to map out the thickness of the ocean floor in accordance to the sediments, and in connection to this thickness of the ocean floor, they be able to connect it with the seafloor spreading theory as what Hess and Dietz is talking about. Alright, so the deep sea drilling project was executed or underwent during 1968 to 1983. So they be able to drill down in the Atlantic Ocean, and some of them are drilling down the Pacific. So they be able to find out, they be able to gather some data after the drilling process, and these are the core samples that they've gathered using the drilling process. So we have here the drill over here, and they be able to obtain these cores, and they be able to study these cores, this course that we have right here, this one, and connect it to the seafloor spreading theory as what the two geologists is talking about earlier. Alright, so in this particular picture, we can say that because of the ocean drilling, they be able to conclude something out of this particular evidence, that as we move from the center, this one is the center here. So this is the spreading center. So as you can see here, this is a typical divergent boundary. So because of this ocean drilling, we be able to have an idea that as we move through the center, away from the center of this divergent boundary, the thickness of the ocean floor, or the thickness of the ocean floor, starting to get bigger. Alright, so then as you move towards the center of the divergent boundary, the thickness becomes less and less. Alright, so it tells us that because of this thickness variation, it tells us that there are new materials that are added and added as time passes by, and as this particular boundary moves from this direction. So as this boundary moves from this direction, you expect that the thicker material will be found away from the spreading center that we have right here. So we can expect that the thickest material is found over here, something like that, much thicker than the one previously that we have right here. So again, the thicker the material, or the thicker the seafloor or the sediments on the ocean floor, the farther away from it, that particular sediment is located from the spreading center. Not only the thickness, but also the age. So the age is also directly proportional to the distance of the ocean floor to the spreading center. So this is the age of the seafloor. So as you can see, as you go farther away from the spreading center, the age of the seafloor increases. So meaning to say, you can find younger rocks at the spreading center and older rocks at the areas which is farther away from this center that we have right here. So this is the two idea. Alright, so this is the two idea that they got from drilling the ocean floor. Alright, so thickness and the age of the seafloor is directly proportional to its distance from the center. Alright, so okay, so in modern times, or in modern day, so we have now modern and advanced equipment. This is the this is a deep sea drilling ship, so we call it CQ. So this particular ship that we have right here is attempting to drill down the oceanic crust and probably be able to reach the mantle, so that they be able to they are now capable of studying it, and somehow if possible they be able to predict how the mantle behaves, and also connect it to where the earthquake will somehow happen, or how the earthquake waves travel on through the mantle. Alright, so that's the GQ. Alright, next. Okay, so that was evidence number 1, the ocean drilling. Alright, so evidence number 2. So in evidence number 2, geologists use the hotspots and mantle plumes in order to predict, in order to identify the movement of the plates. Alright, so do you think that these things, or these hotspot volcanoes and mantle plumes, is it possible that these two can tell us how fast, what is the direction of the movement of your plates? Alright, so possibly. Alright, so what are these hotspots? These hotspots are volcanoes, and these are caused by rising plumes, and these plumes comes from the mantle. Alright, so after the crust, there's a mantle. So this mantle material goes up, and when they go up, they penetrate down the crust, and when they penetrate down the crust, they be able to upwell these materials and then cause some volcanic eruption. Thus, the area contains a volcano. Alright, so basically, these hotspots are volcanic areas. Alright, so since the volcanoes form over them, so one of the example here are the Hawaiian Islands. Very good example. So when this mantle plumes goes up, so this is the upwelling of hot rock coming from the mantle. So it doesn't came from a chamber or some sort of a storage part of the crust. All right. So it came from the mantle itself. Alright, so it came from the mantle itself. So later I will show you a picture what is this hotspot all about. Alright, so some of these originate from the greater depths of the mantle core, or some of them are originating from the mantle core boundary. So imagine that. So if you used to calculate the distance of the mantle down to the crust, so they are very far, alright, or mantle or core from the crust, they are very far from each other. So imagine that these rocks came all the way from the mantle core. Alright, so these mantle plumes are also stationary. So meaning to say that this plume doesn't go anywhere. Alright, so if the mantle plumes doesn't go anywhere, so meaning to say only the one on the crust, if the crust is moving or if the lithosphere is moving, we can hypothesize that if the lithosphere is moving, we can hypothesize that the distance and the direction at which this plate moves. Alright, so since these things are stationary, alright, so and also since they are stationary, they are long-lived. So as long there is an upwelling of this hot rock on that particular area, it will the mantle plume will never stop spewing material from that particular area. So basically, the volcanoes will never stop erupting. All right, just like what is happening on the Hawaiian Islands that we have. Okay, so these are the mantle plumes that we are talking about earlier. So this is the core mantle boundary that we have right here, and because of the upwelling, okay, so because of the upwelling of rocks over here, so we all know that if the material is heated, the material expands. So what happens is the materials becomes less dense, so the rocks over here becomes less dense, then it goes up. Alright, so when they go up, so as you can see here, there are no volcanoes around. Alright, so when these mantle plumes starts to rise, they form a particular spot over here near the lithosphere, which is called the hotspots. And these hotspots is starting to be heated up and starting to break. And once this hotspot or this material that you have right here called the mantle plume starts to penetrate the lithosphere, it will start to flood some basaltic rock on the surface of the earth. Alright, so when they do, they form some volcano, and along the way, when this particular, if the lithosphere moves, there should be a trail of volcano following that particular mantle plume that we have right here. So meaning to say, this trail of volcanoes is only possible if the lithosphere moves. Alright, so this is the Hawaiian Islands. So as you look at these Hawaiian Islands that we see here, we can safely say that the youngest land here will be this one. Alright, so I forgot the name of this island. So this is the youngest, and as you go further from this youngest island here, as you go further away, so this one, so this is the older island. So meaning to say that this island is used to be a volcano before. So because of the plate motion, the mantle plume transferred from this island to this island, and another motion again, the mantle plumes transfer from this island to this island once more, and on the present day, the island or the mantle plume now is now located on this island, big island over here. All right, so basically we can safely say that the continent or that the plate is moving. All right, so the question is how fast and in what direction. So as you can see here, we can calculate the direction. Alright, so we can calculate the direction of the movement of your plates, alright, by simply calculating the distance between the two islands that we have right here. So by just calculating the distance between the two, and the use of distance is equal to velocity times time, so we can calculate how fast the plate moves. And in terms of direction, we can safely say that the plate is somehow moving to that direction. All right, so somehow northwest. All right, towards the northwest. So if this is the Pacific plate that we have right here, so if this is the Pacific plate, so we can safely say that the Pacific plate is moving to the northwest. All right. So at a certain speed, at a certain speed that we have. All right. So that's how you compute, or that's how you use the islands itself in order to compute or find out the direction, and also to compute the distance and the speed of movement of the plate that we have right here. All right. So if you thought that these are the only islands the Hawaii you can see, all right, you are wrong, because that is only, all right, so that is only 4 of the many islands that are formed long time ago as the plate moves. So the one that you see there is only the present islands, all right, present product of this shifting of the plates, shifting of mantle plumes, and along the way there are so many seamounts. These are previously a volcano, but before they become an extinct volcano, they are once part of this mantle plume system. So they used to become a volcano before, but as the plate moves on, the mantle plume shifted and they become extinct. All right, so that's how the Hawaiian Islands look like. All right, under the water. So this seamount that we have right here is underwater. All right, so next one. Okay. Okay, so by measuring or by predicting the age of rocks per island, so by predicting by getting the age of rocks of each island, you'll be able to know the distance and the direction of the plate motion that you can get in this particular hotspot volcanoes. All right, so meaning to say that hotspot volcanoes are very good indicator of the direction and speed of motion of your plate. All right, so these are the hotspots. Okay, and by the way, before I forget, so the hotspot volcanoes are somehow not connected to convergent boundary, and it also not connected to the divergent boundary. So meaning to say, these volcanoes that you see here, are not plate boundary origin volcanoes. All right, so unlike the one that you saw on convergent boundary and on the divergent boundary. And also, to avoid misconception, these are not a product of ocean-to-ocean collision as we have stated last time. So, meaning to say, these things are purely a mantle plume in terms of origin. All right, so that is the hotspot volcano. Not only Hawaii, we somehow have an idea that the Galapagos Islands were once a hotspot before. Okay, so some islands over here in the Galapagos Islands. So if you remember Galapagos Island, these are the islands that were studied by Charles Darwin when he is finding out or formulating the theory of evolution. All right. So if you want to know more, or if you want to find out more hotspot volcanoes on this planet, you can go to this website. So hotspots, geology, wikipedia.org. All right. So it can this particular website will give you hotspots volcano aside from the 2 that I have right here. All right. So that is evidence number 2, the hotspot volcanoes. All right. Next one. The third and final evidence that we have right here is the paleomagnetism. From the word paleo means past, and magnetism, so magnets, yan. So past magnetic data of the Earth. Alright. So one of the most complicated, yet the most persuasive evidence that we can use in order to find out that the plates are really moving. So, okay, so we can use the ancient magnetism preserved in rocks. So this magnetism doesn't change. They are perfectly preserved in rocks, and we can use them in order to identify how far, all right, how far and how fast the plate moves, and also the direction of the plate motion. All right, so we can use this preserved magnetic property of these rocks to find those things. And on this paleomagnetic records, it shows the following things. So the number one is the polar wandering. All right, so what does this statement all about? It tells us that the North Pole is somehow moving relative to the direction of the relative to the position of your continents. But as we all know, the poles are not moving, it's the continent. So later we will try to find it out. All right, and also the times, how many times that the Earth's reverse its magnetic field. So basically, there are times that the south pole of the magnet is underneath or in the south geographic pole, and the north magnetic pole is somehow located in its north geographic pole. So sometimes it reverse. So yeah. Then we have the recorded rocks found in the oceanic regions. So these recorded rocks is somehow a good evidence to find out how far or how fast a plate moves per year. Alright, so let's get started with evidence number 3. Okay, so Physics 101, so the Earth is a big magnet, and this magnet comes from the outer core. So the outer core generates this magnetic field, and we all know that the magnetic field of the Earth helps us shielding through these cosmic rays given up by the sun. Alright, so cosmic radiation given up by the sun. And we all know that the compass, that the white of the compass, which is the north, follows the south of your magnet. So north is attracted to the south of your another magnet. So basically, north repel, south north attract. All right, so just to avoid misconception, the north geographic pole is different from the south geographic, or the north geographic pole and the south geographic pole is different from the south magnetic pole and the north magnetic pole. When we say North geographic pole, literally that's the Arctic. Alright, so that's the Arctic. When we talk about the South geographic pole, that is the Antarctic. Now, when we have the magnetic pole, South magnetic pole, so literally that's the south part of the magnet. And the North magnetic pole is literally the north part of the magnet. Alright, so this is the Earth's magnetic field. And on the rocks, there are some materials called magnetite. So these are some rocks. So these are some materials that are found in these rocks, and this magnetite responds to the Earth's magnetic field. These are just like compass. If a compass responds to the Earth magnetic field, so does this magnetite over here. So the catch here is that when the magnetite is in lava form, alright, they be able to shift their direction. These are the magnetites over here, this arrow that we have. So they be able to shift their direction relative to the present, alright, relative to the magnetic field and at which this lava or lava rocks are spewed out of the Earth. Alright, so meaning to say, on this first layer that we have right here, the present magnetic field direction is going that way. Alright, so on the second layer, so the magnetic field is also did not change. And on the third or rather fourth layer, so there is a reversal that happened. So on that layer of the rock, we can safely say that the magnetite points to the different direction. Alright, so how did they become that way? So at first they are lava. So these lava rocks Alright, so these lava rocks contains magnetite, and this magnetite be able to point themselves to the present magnetic field. Alright, so in this case, the magnetic field goes there, and when the lava cool down, it be able, when it cool down, it entombs this, it preserves this magnetic, or this magnetite going to that direction, and it will never change its direction forever. So, meaning to say, so we can safely say that long time ago, the magnetic field suddenly reversed, and what we have right now on this present day, so in the first layer, are now the present day position of your magnetic field, or where's the north and where's the south pole of the magnet is located. So as you can see on the fifth or sixth layer that we have right here, even long time ago, right? So the magnetic field is somehow the same with the present magnetic field that we have. All of a sudden, it shifted to like what we have right here on this layer, and it shifted again, and what we have here on the present day is now that the south magnetic pole is over here and the north magnetic pole is over there. So because this is the south and this is the north of your magnetite, assuming that is the proper way here. Okay, so with that, we will be able to, with the use of the magnetite that we have right here, that is found on the rock, that is preserved perfectly on the rock, we'll be able to find out some interesting things like this, the one that we have right now, which is called the apparent polar wandering. All right, so from the word itself, apparent, what is the word apparent means? The apparent is what is the actual seen by the eye. Alright, so apparent. Alright, so apparent is different from absolute. The absolute is the actual. Alright, so the actual value. Alright, the actual value that is beyond the eye. Alright, so meaning to say, what we have right here is the apparent polar wandering tells us that somehow the continents really move. Why? It's because it tells, this particular part tells us that the poles suddenly shifted, alright, along the way. So, very unlikely, but in this particular data that we have right here, so this is the position of those poles relative to the continents, that they have. So for example, the green one is for the Eurasia and the red one is for North America. So in North America, alright, so in North America, 100 million years ago, the position of the North Pole in North America is towards here. Alright? And in Eurasia, 100 million years ago, the position of the North Pole is here. So, after 200 million years, the position of the North Pole is here and there. Then, after 500 million years, so the position now of the North Pole is over there. Alright, so the position of the North Pole relative to the continent that they are, that the continent is pointing them. Alright, so what does it tells us? It tells us that over time, the continents shifting their places, and when they do, so if we trace back this apparent polar wandering that we have right here, if we go back again to the original form of the continent, which is the Pangea, so we can safely say that the data that you gathered here on the present position, alright, so on the present data that we have right here, if you connect them all together, we can safely say that the continents are moving. Alright, so that the continents are moving. So these are the relative position of the poles, these are the position of the poles relative to the position of your continents that we have right here. It is not the pole that is moving. It is the continent. But apparently, it looks like that the pole is moving. So the word is apparent polar wandering. So please take note that only the continents that are moving, but we can assume that the poles apparently moves relative to the position of the continent. Alright, so okay, so to better visualize this one, so I have right here, so for example, that the continents is separated by a ridge. Alright, so as the ridge move away from each other, or the continents move away from each other, so we have continent A over here, so we have continent B over there. Alright, so continent A, alright, so continent A, the rocks in the continent A, the magnetite especially, is pointing that the North Pole 200 million years ago, is somehow located at this point. Alright, and on continent B, the magnetites there, upon gathering the data, is located at this particular point, 200 million years ago. Alright, so very unlikely, but it is impossible to have two North Poles, right? Alright, so okay, we can go back in time. We can go back in time and trace out what if we put the two continents, these two continents together. Alright, so if we put them together once more, so we can predict that this one and this one also, or this pole that we have right here, will also is also connected to each other. So it will likely look like this. So continent A, then this is your continent B. So they are pointing at the same direction. So probably the North Pole during their time before they got separated is located at this point. Alright, so at this point. So when they got separated due to the continents, due to plate tectonics, alright, so the data that we gather right now at the present day is, it appears, the word is appears, it appears that there are two poles, but that is impossible. So we can safely say that the polar regions apparently moving. Alright, apparently. So there we go. That is the apparent polar mandate. Alright, so let's go to the next. Alright, so again, there are we have two scientists here. They be able to create something, and they have an idea that these particular reversals can be found underwater. So Fred Vine and Drummond Matthews developed or conducted an experiment, and this experiment was done in the Pacific. So they mapped out the ocean floor in the Pacific using their instrument called magnetometer. Alright, so this magnetometer that we have right here. So this magnetometer is very sensitive to the magnetic anomalies found in the rocks. Alright, so this magnetometer is an instrument used to detect magnetic field found in rocks. Alright, especially these magnetites that we have right there. Okay, so using this magnetometer, they be able to track down in which time that the magnetic reversal happens, and be able to calculate the distance that the particular plate boundary moves respectively. Alright, so this magnetometer is attached to a ship, and as the ship moves this way, alright, as the ship moves this way, the magnetometer is scanning the ocean floor for this magnetic anomaly. So that is the magnetometer used by these two guys that we have right here. Okay, so after the process, they be able to map down the ocean floor. So this is the data that we have right here. Okay, so this is the middle line. So this is the middle line. So this is the x-axis, and this is the y-axis over here. Alright, so as you can see here, the peaks above the x-axis, these are the rocks that follows the present magnetic field. Alright, so these are the peaks that we have right here. Okay, so the peaks that are below these negative peaks that we have right here below the x-axis, all right, these are the rocks that do not follow the present magnetic field. So meaning to say, this is these rocks that is detected at the peak below, these are the rocks that is repelling, all right? So somehow they are repelled by the present magnetic field, and the ones that is on above, these are the ones that are attracted to the present magnetic field. All right, so as they do that experiment, they be able to found something, they found something more profound than the thickness and the age of the ocean floor. All right, so they be able to find out these particular segments that we have right here, these magnetic segments, and they be able to calculate how fast the continent moves, somehow precisely. All right, so as new materials erupt from the spreading ridge from the ridge that we have right here, as we all know, there is a volcano here. As new materials erupt from that ridge, it spews out new rocks, and these new rocks contains magnetite. And once the magnetite detects the magnetic field of the earth, they be able to align themselves on that magnetic field. So these are they now, and as a new rocks erupt from this particular ridge, they be able to find again that magnetic field. So as they move away, as we have on the ocean drilling process, as this rock move away from the center, the age of the rocks increases. All right, and also as this move from the center, the thickness also increases. And not only that, if there's a magnetic reversal, so if there's a magnetic reversal happened along the way as these rocks produce, so this particular reversed magnetic field is also detected by the magnetite, for example, that we have right here. So maybe on this date, on this year, or on this timeline, the rocks somehow detected the changes in the magnetic field. So meaning to say, it will likely that the rocks here has different orientation of magnetites than the one that you have right on this side. Alright, so as it continues to progress, as it continues to produce more and more rocks from the ridges, it will encounter this magnetic field, this magnetite from these rocks that is produced on the ridge will encounter these changes in the magnetic field. So whatever magnetic field lines that they are detecting, so meaning to say they are these magnetites will just follow them through. All right. So in a normal polarity of reversals, so in a normal polarity, the north magnetic pole is connected or is positioned in the north geographic pole. All right. So north. So next one, the south magnetic pole is positioned at the south magnetic pole. Alright, so, or the south magnetic pole is positioned at the south geographic pole. So that is the normal polarity. Now, if magnetic reversal happens, alright, so it is now called the reverse polarity, in which the south magnetic pole is located at the north geographic pole. So the white part of the compass will point here. Alright, so the white part of the compass. Then the north magnetic pole is located at the south geographic pole. So this is what they call the reverse polarity. So maybe after 100,000 years or after 500 years, this magnetic field will shift. So they are not permanently there. They will shift after 500 years or after 100,000 years, something like that. So they will shift again and shift and shift and shift. So basically, our magnetic field will reverse all the time. Alright, so will reverse all the time as time passes by. Okay, so these are some thermographic image of reversing your reverse magnetic reversal that happened. Yan. So as you can see here, the red spot over here is starting to shift. Alright, it is starting to shift from south. So after the shifting process, it is now, the red material here is now located at the top, which is on the northern hemisphere now. All right, so we can detect them using infrared images. Okay, so next one. So as I've said earlier, yan, if the is newly erupted from the Earth. So the magnetite have chance to align themselves to the magnetic field. Now, when they cool down, the one at the bottom, so when they cool down, they are preserved perfectly to the present magnetic field when they encountered it on the first place. Alright, so meaning to say we can use the rocks, we can use the magnetites in on the rocks as some sort of time machine. Alright, as a timeline or time machine, which we can try to predict which way that the continental plate or the plates move rather. Yeah. Okay, so that is the magnetic reversals. Okay, so what do we have right here? Okay, so the normal polarity is on the top and the reverse polarity is on the bottom. All right. So all right. Okay. So this is another picture of this normal polarity and reverse polarity that happened on the ocean floor somewhere near the United States in the Pacific Ocean, and we can see some symmetry here. So what happens on the right is the same thing on the left. All right, so it is very impossible to have two sets of polarity which is different from each side that we have right here. Okay, so indicating this normal polarity that we have right here, indicated by white over here and red for the reverse polarity, we can safely say how fast, or we can safely compute how fast that the continent moves or that the plate moves, and how what is the direction of their movement. Okay. Okay, so as time passes by, this accumulation of new materials coming from the ridges, and these new materials contains magnetite, align themselves to the magnetic field, preserve them, and as we gather some data on this preserved magnetite that we have right here, we have now an idea that really a concrete evidence that the continents are moving. All right, in a constant or somehow constant speed or in a relative speed. All right, so based on this magnetic data that we have right here. Okay, so just so you know, only the magnetite, all right, only the magnetite that we can use here, or we can use the magnetites from the rocks in order to find out this movement of your plates or plate tectonics that we have right here. Okay. So the question that we have right here is how the plate motion is measured. All right. So the plate motion is measured by one thing. One is the use of hotspot, as we discussed earlier. And as of now, as human technology advance, as time passes by, we be able to also advance our way of measuring this plate motion. So we have now the very long baseline interferometry and the global positioning system. I know you are familiar with. All right. So the very familiar that we discussed at first is the hotspot motion. I've already discussed that one by the use of the distance between the two volcanoes, and computing along that distance, you can measure measure the plate motion, and also not only the plate motion but also the direction of its movement. Now, what are these space age technology? So basically, we can measure the plate motion from space. All right. So these satellite things that are moving or orbiting around the Earth, we can use them in order to measure this plate motion. All right. So the first one is the VLBI, very long baseline interferometry. Now, in this technique, so we will use some distant objects or heavenly or celestial objects like this, like the one that we have right here. We called it quasars, and we all know quasars emit radio waves. All right, so these quasars emit radio waves, and these radio waves are captured by our radio telescope here on Earth. Okay, so these telescopes that we have right here are called radio telescopes, and these radio waves are captured by these instruments that we have right here. Now, how is it done? All right. For example, there's a continent over here. All right. So there's a continent over here, and there's a radio telescope over there. All right. So if the quasar, so the quasar is over here. All right. So if the quasar is emitting a radio wave, all right, is emitting a radio wave, it will be picked up by, all right, it will be picked up by the radio telescope over here. All right. Now, what if the continent suddenly shift? All right, what if the continent suddenly shift, or we can put it right here. All right. So what if this continent that we have right here suddenly shift forward? All right. So how will we be able to compute the how will we be able to compute the motion of the plates? So simply by using the radio telescope that we have right there, the same radio telescope. So it will be pointed out again to that quasar, and the quasar will emit a radio wave. So since the quasar somehow doesn't move, all right, so relative to that position, it will be picked up by the radio telescope. Then with the discrepancy or the differences in terms of distance of the radio waves that is gathered before and after, so with the use of trigonometry, so they be able to compute how far the plate moves after the after the motion, or after an earthquake, something like that. Okay, so with the use of this very long baseline interferometry, we be able to somehow accurately or precisely compute the relative motion of the plates. Okay, so again with the use of the trigonometry. Okay, so next one is the global positioning system. All right, so there are in every continents on Earth there are satellite systems that are connected to this. There are towers that are connected to these satellites, and these towers are somehow connected to these satellites over here, which is used to compute the, or sabi natin, we can safely say that we can say that these satellites, right over here, is connected to those towers. And when the towers on this continent, for example, I have one right here, when the towers are somehow moved because of this plate movement, okay, so that the satellites will be calibrated again in order to connect on that tower. And once they are calibrated, they be able to compute the direction of the motion or the direction of movement, and also the speed of the motion of that particular continent. Okay, so whenever a tower that is connected to this GPS satellite is moved, it is always calibrated. All right, so that is why it is very important for the global positioning system to be accurately calibrated, so that we will this particular satellite, they will be able to track down where we are on planet Earth. All right, so that is the global positioning system. All right, so because of those technology and techniques that we mentioned earlier, they be able to find out the movement of the plates what we have on this picture. So, for example, this mid-Atlantic ridge is somehow moving 3.5 cm per year. All right, so on that direction. All right, so the African plate is somehow moving 2.6 to 4.1 centimeter per year on that, going to that direction. And the Philippine plate that we have right here is somehow doing some convergent things that we have right here, is converging on that side, and it is somehow moving 2.6 to 4.1 cm per year. So the largest motion is somehow the Pacific plate. So in this case, it is moving around 7.0 cm per year. How about the Australia? The Australia is moving 4.1 on that direction. So with the use of the technology that we have right there, not only the technology but also the techniques by using hotspots, hotspot volcanoes, we be able to track down the motion of these plates, and it gives us an idea what will be the motion of these plates in the future. What will our continents look like in the future if the plate motion continues. All right. So with that, that ends up our video lesson for testing the plate tectonics model. All right. So I hope with these particular evidences and techniques that I have discussed here, you'll be able to know that the continental drift, all right, that the idea perceived by Alfred Wegener long time ago, all right, is somehow true and valid. All right, only the drifting there is rejected, but as he said that the continents are moving, so basically based on these evidences and techniques that we have here right now, so we can safely say that he is true all along. All right, so well then, so that ends up our video lesson. So I hope you did learn something from this one. All right, so you can comment down, you can write your comments, or you can type your comments on the comment section if you want, or if you want some, or if you're going to ask some question, type it down there. All right, so that's it. So we'll see each other again. So goodbye, and always smile.